morning and welcome to the next edition of our Colloquium talks. It's a pleasure to welcome Sawyer Fuller from the Department of Mechanical Engineering here at UW. Sawyer's research focuses on biologically inspired sensors, control systems, and mechanical designs targeted at insect-size air and ground vehicles, and he investigates the flight systems of aerial insects. Sawyer received the PhD in biological engineering from the California Institute of Technology, Caltech, and the bachelor's and master's degrees in mechanical engineering at MIT. In addition to his work in insect flight control, he also developed a frog-hopping robot at NASA Jet Propulsion Lab and invented an inkjet printer capable of fabricating millimeter-size 3D metal machines at the MIT Media Lab. Sawyer's work has been featured in a cover article in MIT Technology Review and in news outlets such as Wired, The Scientist, and prestigious journals such as Science and Proceedings of the National Academy. So it's a pleasure to welcome Sawyer. Thank you very much for coming to speak with us.
So can you hear me? Yeah, okay. Thanks, Matt. Thank you all for coming to listen to me. So what I'm going to talk about in this talk today is this task of how to create an autonomous flying robotic insect. And what I'm talking about with that terminology is a robot about the size of a fly or bee that has a sensory input capability to fly itself through the air and carry out useful tasks without a human operator. In other words, a robot fly that looks something like the robot on the right, but also has the sensory systems, power, and control systems of the fly on the left. So you have a mental image of what I'm talking about. This is a recent incarnation of a robotic fly, and it's about the size and weight of a honeybee. So why would you want to make a flying robotic insect? I'll start with that. The reason is that a robot fly has a number of kind of a combination of capabilities that are not shared by any other class of robots. So for example, they're small, so they can fly in confined spaces. They are airborne, so they can cover almost any terrain, which represents less of a limitation than if they're ambulatory, for example. And they can, because of their small size, they have low materials cost, so they could potentially be deployed in large numbers. This suggests applications in environmental monitoring in locations like in agriculture or in industry, or even in the home. So to kind of motivate a specific case, I'd like to give an example. So suppose you had a suitcase full of these flying robots, and each of which was equipped with a sensor that was capable of detecting natural gas. You could open the suitcase up, these robots would fly out, and they would start searching for the gas. Maybe as they searched, they would perform obstacle avoidance, navigating through the world, perceiving it. And then once the gas was detected, they would do an insect-inspired plume following algorithm to localize the source of the plume, just like an insect, and then land at the source and possibly emit a beacon that then a human operator could then find and use to then later plug the leak. So if you had technology like this that made it easy to find leaks, then this could potentially reduce emissions of greenhouse natural gas, which is a potent greenhouse gas. So there's another motivation for building insect robots, which is that the constraints of insect scale will drive innovation in the area of miniaturization to find solutions to miniaturization. So for example, there's a whole stack of components that need to be miniaturized on a robotic fly. This includes everything from how do you manufacture them, how do you control them, how do you sense, and even how do you navigate. And these all represent unsolved engineering challenges. So you might say, isn't this already a solved problem? You can already buy quad rotors like this Parrot AR drone at the store for couple $100 right now, and they can fly themselves just fine. Why not just take all the components of this quadrotor drone and shrink them down to the size of a fly, and then you're done? The answer is that you can't just do this, and the reason for this is that the physics of scaling gets in the way. So especially as you start getting down to the size of a fly, a lot of your basic intuitive engineering assumptions, especially in robotics, start to break down. Because of this physics of scaling. Because of the physics of scaling, different effects start to dominate. So for example, on the side of mechanics, spinning things like pin joints start to become very inefficient because of the increased importance of surface effects like Coulomb friction. And propellers and gliding is also inefficient because of the increased effect of viscosity at insect scale. So for example, when the exponent is negative, that makes things large at small scale. So this is unfavorable to propeller-driven and gliding flight. On the side of sensing, you also have additional challenges. Many workhorse sensors, including the global positioning system and, say, radar, laser rangefinders, and so on, become very impractical. In the case of GPS, the resolution relative to the scale of the robot gets worse and worse as you go smaller, and it's in fact denied indoors. And you have a very limited battery power as you go to small scale. So you're restricted to primarily non-emissive sensors. And this extends to control as well. As you go to small scale, rotation speed increases, while computation becomes more constrained. So taken together, what these all suggest are a lot of fundamentally new approaches are going to be needed to solve the problem of miniaturization down to insect scale to achieve the sort of autonomy I'm talking about. So one promising approach that I really like is to look to insects for inspiration. For example, small flying insects like flies, which are one of my favorite animals, continually flap their wings rather than glide like birds. And this is an adaptation of the greater effect of viscous friction as scale diminishes. But more than that, we can look to flies for further inspiration, not just for scaling solutions, but for their supremely agile capabilities in flight. These are among the most agile insects on Earth, and they are this way because of their ecological niche, which is to avoid predators that like to eat them. They have no stingers, they taste good, so they have to rely on their speed instead. And they're also quite good at landing, as you can see here. Their capabilities are really at the forefront of a lot of fields, everything from material science to control theory to fluid mechanics. And while much has been learned about their flight apparatus, little is known about how the different components work together. But I'll tell you a little bit about their flight apparatus before I move into building insects, robots inspired by them. They rely on a number of pretty sophisticated sensors, including gyroscopic halteres to measure angular velocity, ocelli to measure which way is up relative to the sun or sky. They have a pair of antennae that are kind of a sensory center, sensing everything from wind and smell to gravity. And they have a pair of large compound eyes that take a low resolution but nearly omnidirectional snapshot of the world. So we still don't know how to make robots that do anything like what flies are capable of doing, but they serve as inspiration and also our performance target for future engineered systems. So in this talk, I will now give you a series of milestones that have been achieved so far and future milestones, many of which I've been a part of, aiming to build a useful robotic fly. So I'll start from the beginning. The first task was to demonstrate sufficient lift in a fly-sized package. Following that, it was necessary to incorporate some sort of control system, ability to control the flight to achieve controlled hover. In both of these cases, the challenge was fabrication that was compatible with insect scale. Following that, a next challenge was to begin adding some sort of sensory systems to the robot so it can start to remove the need for tracking cameras and start perceiving the world itself. Here, the first step was to add a sensor that had the capability of stabilizing the inner loop attitude dynamics. Along these lines, I will take a brief interlude to talk about exploring the kind of expanded maneuvering capabilities of small scale. And the challenge in this case is that the dynamics get faster as you go to small scale. Following that, the next step to achieving full sensor autonomy is to achieve full sensor autonomy, which is to say being able to perform controlled flight using only sensors on board without the need for these external tracking cameras. So many, as I mentioned, many of the sensor technologies available for larger mobile robots aren't applicable here, leaving vision as the best remaining candidate. And the challenge here is that while vision is a typically computation-intensive task, the power budget for the computations to be performed at this scale is very low, on the order of 10 milliwatts, which is 2 orders of magnitude less than a typical cell phone processor. So I'll talk about possible solutions here to this computation limitations challenge. I'll give a couple of vignettes at the end about how to land the robot and also how to power the robot. And in both of these cases, surface area scaling may help in terms of making new opportunities which weren't possible at larger scale robots. So some of these have been achieved in demonstration form, which I'll show you, and others remain open challenges. And the common theme, again, is that small scale has required new solutions because of the changed physics. Sometimes new technologies are required to overcome the challenges, but other times new capabilities emerge because of small scale. And often solutions have been found by looking to biology. So first, how do you get enough lift to take off? So the story with making the first insect-sized robot capable of taking off starts with a history of small aerial vehicles. In many cases, these robots, the engineering approach was to build a large robot and then progressively shrink it down. This was demonstrated by a 3-gram Prox Flyer, which started life as a much larger robot. Similarly, the Delphi Micro started with a 30-centimeter wingspan before moving to 10 centimeters. The Nano Hummingbird as well. Let's see. In a notable departure from this approach, Ron Fearing at Berkeley set out in the late 90s to build a robot fly starting at the target scale of a fly rather than trying to shrink down. And one of the central ideas he realized was that because of the scaling physics, he knew that he would have to use a different actuator type than the electric motors that have been used successfully in these larger robots. This immediately suggested piezoelectric actuators, which are driven by electrostatic forces, which scale down more favorably to small scale. Their linear displacement naturally leads to flapping wings rather than spinning propellers. After a few years, they had developed a prototype that looks something like this, the Berkeley microrobotic insect. It was able to flap its wings at the correct frequency, about 100 hertz, but it wasn't able to lift its weight. Later, at Harvard, one of Ron Fearing's graduate students, then a professor, came up with a nice solution, which was to, rather than control the complete kinematics of the wing, which they had been trying to do at Berkeley, was to instead only control the stroke angle and allow the angle of attack to rotate passively. This vastly simplified the mechanism and allowed the first demonstration of lift to weight greater than 1. The other key success story of this of Fearing's micro-robotic fly project was the development of a new laser-based fabrication process that was greatly advanced in Rob Wood's group. It consists of cutting relatively thin layers of material using an ultraviolet laser with a 355 nanometer wavelength, and then laminating them together under heat and pressure and pin alignment to form flexure-based structures like this on the lower left. This laser cuts with about a 10 micron spot size and is able to cut almost anything. So you can start to make parts out of very high performance materials like aircraft grade carbon fiber and aluminum, for example. And parts take just a few minutes to cut, so this allows for a very rapid design iteration. To give you an idea of what's possible with this, I wanted to show you a video of some work that I wasn't involved with, but I think it's pretty impressive. This is Popup Assembly. The basic idea is to fold all the components together in a single motion using a scaffold inspired by origami, with a single degree of freedom, and then gluing the components together after they've been folded, and then releasing them. This allows some very good alignment capabilities and makes it very fast to build them. Here's an example, but for practical reasons, it's actually still a little bit easier for prototype development to assemble them by hand. So that's how I'm going to be doing it in the short term. And so here's a current robotic design that was hand assembled, a little more flexible at this point. Designed by Kevin Ma in Rob Wood's group. As you can see, the parts are quite intricate inside. This is an exploded view. You can see here the two cantilever piezo actuators. And they move very small amounts, and that drives a lever arm to move the wing with a very large amplitude. So to give a sense of scale, here it is being assembled under a microscope. That's a gloved finger there in glue. We have a term for this in Rob Wood's group, which is the GSWT manufacturing process, which is grad student with tweezers. Let's see. So that's assembly. So that gives you an idea of how to build these guys. Now I'll get into how to do controlled hover once sufficient lift is achieved. So controlling flight requires a method of actuation. So this is using this improved design I just showed you. It has independently actuated wings, as shown by this video on the right. And this allows it to control roll and pitch. So for example, to control roll, one wing is flapped with a larger amplitude than the other. To control pitch, the mean stroke angle is moved either forward or aft of the center of mass. So that's the control side. Then for the sensing side, I set up this motion capture arena with a series of cameras to triangulate the position and orientation of the robot. And this is fed into a control computer that does some control magic to make it actually fly. This is what the flight arena looks like. There's the robot down at the bottom. That's a quarter for scale. And you can see the cameras up there, and there's also a bank of computers over to the right that you don't see in this picture. The control architecture, I worked with another graduate student, Pakpong Chiraratananan, to devise a controller for this robot. The basic architecture is it uses an inner feedback loop an attitude controller that assumes a linearization of the dynamics around hover that operates separately to control altitude controller, which is just a PID controller, and then an inner attitude controller that controls the orientation of the robot, and then an outer lateral controller that commands tilt angles to that inner attitude controller to perform lateral maneuvers. Feedback comes from a set of cameras that are operating at about 500 frames per second with a 10 to 15 millisecond latency, and a desktop computer is performing these computations. So this is what it looks like in flight. And it's performing a simple lateral maneuver. Lateral maneuvers are achieved by again, tilting the robot, much like a helicopter does to add lateral thrust. So this represented a significant step because it showed that the fundamentals were in place as far as manufacturing, but it also highlighted the next steps, which were to add sensing, computation, and power on board. So it looks like a flying insect, but it's only doing part of what insects do here. So now I'll move to the next step, which is how to achieve, start putting sensors on board. And here, what I showed, so here, what I'll talk about is giving the robot attitude stability. So the video I just showed has this kind of magical appearance of the flying perfectly, but it doesn't look anything like that when you don't have that controller running. So let me show you now what happens when you turn on the wings without any controller. I'll stow it in real time first, so it happens very fast, so don't blink. Okay, and then I'll play it in slow motion. One nice thing is the small scale makes it quite a bit more robust, so it doesn't really matter if you crash it like this, up to a point. So the challenge here is that the robot has dynamic instability. So the first step toward sensor autonomy is therefore to incorporate some sort of sensor on board that can compensate for this instability so that the robot can stay upright on its own. So consider the dynamics of a simplified planar model of the robot. The wings produce thrust. The center of mass hangs below, something like this. If there's a lateral velocity, the fly is drifting to one direction or another, then air drag starts to act on the robot. And because the wings are quite a bit larger than the body of the robot and they're moving much faster, the drag force acts primarily at the wings. Let's see. This air drag produces a self-righting effect. So if the robot is tilted to the right, it starts to move to the right. Air drag causes a righting effect. This video shows the idea. The robot tilts first left, the drag acts, then it flips, and then it kind of flips over on the other side. So this is a growing dynamic instability in the dynamics. Yeah, it's a growing sinusoid oscillation. So it's pendulum-like dynamics, but it's a little bit different. So then I performed wind tunnel tests to try to nail down what exactly is going on here. And I found this nice fact that drag is roughly proportional to airspeed, which kind of makes sense if you go look at the dynamics. The wing drag goes as the square of the airspeed on the downstroke, but also as the square on the upstroke. And if you do the quadratic formula and subtract those two, you end up with a linear effects remaining. So then so this is the drag force model. Then I plug this into a dynamic simulator that gives very similar behavior. So suppose now you can come up with a feedback controller that can stabilize this. Suppose you add a feedback controller that applies a torque in proportion to the angular velocity of the robot. In other words, one that adds rotational damping. In this case, the controller would be performing actuation by changing the wing kinematics to apply the desired torque to implement this control law. I derived this linear model for the dynamics and used the Routh-Hurwitz stability criterion to find a closed form solution to the minimum gain or damping necessary to achieve upright stability. And the model indicates that if the robot's angular velocity can be measured somehow, then it can be stabilized using this proportional feedback law. So to measure angular velocity, I then turned to insects for inspiration, and an approach that's compatible with the low sensor payload ability of the robot. So in addition to the compound highs, as I mentioned, many flying insects have 3 light-sensing ocelli on the tops of their heads that are believed to sense the direction of the sun or sky with a rather faster response time than the eyes. So they are thought to act as stabilization organs. But they actually play has not exactly been explained or conclusively demonstrated. So I took this as inspiration and worked with a colleague to design this folded 4-pixel camera that's inspired by Insectocelli. And the idea is, in a 2-dimensional case, as this sensor rotates back and forth, the 2 light sensors pick up more or less of, they're very, very defocused light sensors, as shown by this wide acceptance angle. So as this sensor rotates left or right, one or the other of the light sensors picks up more or less light. By taking the derivative of this difference, a crude estimate of angular velocity can be computed. And as you can see in this plot, the estimate follows the true angular velocity in this oscillation experiment as captured by the motion capture cameras. It does a well enough job for control, let's say. So then, using this sensor, I went to close the feedback loop, using this sensor to sense rotational damping, and then flap the wings to apply that rotational damping. So just to reiterate, without feedback, the fly quickly tumbles. And then with this sensor feedback algorithm implemented, the fly is able to stay upright and fly up like that rather than immediately crashing. So this is the first time any sort of sensing can be deployed on a robot this small. Going one step further, I added a gyroscope from a mobile phone onto this robot and used it to enable short hovering flights in which the inner stabilization feedback was provided by the gyroscope, whereas the motion capture only provided position information. So I also want to talk about how high-speed dynamics represents both a challenge but also an opportunity for kind of new modes of flight motion and really fast maneuvers. So if you look at a rough scaling analysis, it shows that the angular velocity, as I mentioned at the beginning, the angular acceleration can increase with decreasing scale. This is because with a crude scaling argument, you can show that torque goes roughly as the wingspan to the 4th, whereas moment of inertia goes as to the 5th, so acceleration goes faster as you go smaller. So to demonstrate kind of what you can do with this, this is a demonstration of Lie bracket motion. If the robot makes a series of pitch and roll rotations in quick succession, the result can be a net rotation around the z-axis. This is known as Lie bracket motion. And here it is happening at 10 hertz in real time. So this is sort of like when you draw circles on the screen in CAD software, you can cause the object to rotate on the screen. Here it is in slow motion. So as you see, it's just wriggling very quickly, and this allows it to rotate around a third axis. This is the sort of thing that would be very hard to do in quadrotor helicopters because they're much larger, so they have a larger moment of inertia. And in fact, it's also even slower than that because helicopters have to spin up and slow down their motors, whereas flapping wing robots like this one can change wing strokes on a stroke-by-stroke basis. So I'm very excited to explore further high-speed motions as suggested by this. So now I'll address how we might bring enough sensory feedback on board to allow the robot to fully sense and control its flight in the environment. And as I mentioned, because other sensors are too heavy and unavailable, this really leaves primarily vision as the workhorse sensor here. But heavy computations, like what you might need to do relatively successful simultaneous localization and mapping algorithms in larger robots, really are probably not possible at the 10 milliwatt power budget of an insect scale microprocessor. So a possible alternative approach is inspired by the techniques thought to be used by flies. So flies, electrophysiological studies on flies have shown that they, at least one of the cues they use to control their flight is this pattern of optic flow. So optic flow is a measure of the angular velocity of objects moving through the visual scene as the camera is moved through the visual scene. So for example, if a camera is moving forward down this scene, down the sidewalk here, objects that are moving fast, like this tree, moving fast and are close, have a large optic flow, where objects that are farther away have a very low optic flow. So this represents a rich source of information about the geometry of the world. And flies likely use this information to do things like avoid obstacles or regulate their flight speed. So in graduate school, I got very interested in how to do control using this basic idea in an actual robot. So I built this hovercraft robot to perform visual navigation in confined spaces using raw pixel readings. It was equipped with a omnidirectional camera and a pair of differential fans. So between each pair of the omnidirectional camera is actually this black round thing at the top. Between each pair of sensors, it performed a delay and multiply operation known as a correlator, which computed a crude estimate of optic flow. And then on a high level, what it does is maneuvers by, for example, turning away from looming patterns of optic flow, as you can see in this video here. So this resulted in a very nice visual navigation algorithm that used very little computation, less than 20 kiloflops, which is negligible compared to what even a cell phone processor can do of gigaflops these days. But one of the challenges I came across is that estimates of these parameters from optic flow, such as, for example, forward velocity, turned out to be quite noisy because of this crude operation. As you can see, the red line is quite a bit noisier than the true velocity as measured by overhead cameras. So one solution is to just take a moving average of this wiggly signal, but the problem with that is that this slows down the feedback loop, because then you basically incorporate a time delay because of this moving average averages things from previous times. So then I got interested in how the fly, presumably the fly has the same problem, and how does it solve this problem? And the noise was okay to tolerate on this larger robot because the dynamics were so much slower. But as you got down to the insect scale, this potentially would be a significant challenge. So flies definitely perform some sort of flight speed regulation based on optic flow. This was very adeptly demonstrated by this classic experiment done in the 80s, where Charlie David flew flies down a wind tunnel and measured how fast they flew as a function of the speed of the air blowing through the wind tunnel. And what he found was that the flies basically flew exactly the same speed regardless of the strength of the wind. And this strongly suggested that they had a very tight feedback loop using vision to regulate their flight speed to overcome the effect of this large variation in drag from the wind. So then I started doing experiments where I started perturbing these flies with gusts of wind to get a better sense of what's going on with the dynamics of this visual feedback regulator. So this is a video I took of a fruit fly. And what happens is right about here, I apply a gust of wind to perturb the dynamics. This is slowed down by about 200x. So as you can see, the fly slows down, and then a short while later, it starts to recover its initial velocity. This is an impulsive gust of wind, so it only lasts for about 7 wing strokes. So to get a little bit better understanding of what's going on with this, I started recording their flight trajectories using motion capture cameras and an apparatus that looks something like this. So as the fly moves down this wind tunnel, this air piston driven by a linear motor blasts it with gusts of air. Here's a video of the air piston. So air piston moves really fast because the fly has a very fast feedback system. So that's the blast of wind. Take data for about a day, and this is what you get of the trajectories of the fly flying around in the wind tunnel. This is an overhead view. So then I also played a little trick on the fly. In addition to the gusts of wind, I actually animated this background pattern that the flies were seeing as they flew down the wind tunnel. And what I found is that, first of all, they do respond very strongly to this pattern of visual motion, almost perfectly, faithfully reproducing a visual stimuli, but with a pretty significant delay. So this confirms the notion that they're probably doing some sort of time averaging to compensate for the noisiness in their visual feedback system. So to get a better sense of this, what's going on with the wind sensing and visual sensing, I wanted a quantitative model of the fly. So I spent more than a year collecting data from the fly as it responded to different combinations of wind and visual stimuli in different directions and different speeds, and proposed the following model for its feedback regulator. So the fly has a mass subject to thrust driven by wings and air drag acting on the wings. And then this inner simple model is then the plant in an outer visual feedback loop. And so the identified model of the visual feedback regulator indeed has a relatively large delay of about 80 milliseconds, as well as an integrating term to compensate for the wind drag, for example, for constant wind. What happened when I simulated this model using the parameters I found from system identification was that the dynamics were nearly unstable. And this was because there was a relatively high gain coupled with a long feedback delay in the visual feedback loop. What the wind gusts then revealed was that the fly actually incorporates the reflex driven by the antenna actually is basically an additional damper, almost about equal to the air drag. And what this damper does, it acts with a much shorter delay, but it basically eliminates these oscillations and makes the fly's flight much more stable. And so this gets the fly two things. One is it gets it more stability, but it also means that the fly can operate its visual feedback loop with a higher gain, allowing it to be much more agile. Josh?
Is it mechanical, or is it the neural signals, or do we not know at this point?
So the question is the delay mechanical or neural? And the answer is, this is a good inquiry for future work. Generally, in the case of flies, mechanosensory signals are much lower latency than visual signals are. But my hunch is that it's probably doing some sort of averaging as well on the mechanosensory side to compensate, to smooth out noise. That's probably where the delay comes from. Yeah, question?
Are you able to reproduce the underdamped transient by cutting the antennas off the fly?
Yes. Yeah, I don't show that data. So the question is, do the flies actually exhibit this oscillation? And they indeed do. I didn't show that data, but they fly around the tunnel like they're drunk, which is kind of cool.
But did you get that same step response that you predicted to a perturbation in light?
That would be a nice experiment to reproduce this. I saw this in rough form because the experiment consisted of a step input, and you do see this. It's more of an anecdotal, but I see this kind of overshoot behavior that I don't see with the flies that are intact. Yeah, good question. So if we were to take this and bring it back to an engineering insight for robotics, I want to show you this video of a drone equipped with a camera looking downward that is stabilizing its location using onboard visual processing. And what you see is that it's doing quite a good job, but you'll notice it's kind of doing this kind of wobbling oscillation there. And that's because there's this time delay caused by computation and potentially noise integration. And so what these results in flies suggest is that potentially this drone could do even better and stabilize its position more precisely without these oscillations if it additionally incorporated a wind sensor. So what this means for the robotic fly is the following. I would humbly propose the following control architecture for a robotic fly that incorporates these findings. It would have a omnidirectional camera. Doesn't look like that, but you can buy these full global shutter cameras that are very tiny now. Put a special lens on, you could get nearly omnidirectional vision with that. Combine that with a coarse but efficient optic flow computation using delay and multiply correlators. And as I mentioned, this leads to a relatively coarse but very efficient computation of optic flow. And then compensate for the need to do time averaging by additionally incorporating this wind sensor to add the damping to the dynamic system so that it stabilizes it. So the idea is here, battery is still off-board, but we've brought the computation vision on board. And I've already started developing wind sensors that could be deployed at this scale. So this remains open future work. Then I'll touch on a few other last thoughts. So as I mentioned, one of the things you might want to do is to be able to land. This is very valuable because then rather than flying continuously, the robot could then potentially stay in one place on elevated structures like trees or buildings and do the sort of things it might want to do, like wireless networking or smelling or monitoring things. So here is a demonstration of landing using taking advantage of the small scale. So in this case, a electrostatic patch is attached to the top of the robot. And there it goes using electrostatic adhesion. It adheres to a leaf. To take off, all that's required is to turn off the voltage at the end. And especially if you can hang under structures like this makes you more protected from the elements. Let's see. Lastly, how can this robot be powered? So I just wanted to suggest one modest proposal, which is that it might be powered by solar. And this is another example where the small scale really helps out. So the problem in many electric drones is that they have a very limited battery life of only maybe 30 minutes. But suppose instead we could power these drones with solar power. Well, if you look at a popular drone, this Parrot AR drone, and you look at the solar cell you'd need if you assumed maybe a half sun and 20% efficiency solar panels, you need quite a large solar panel. This could be problematic because you both have extra weight and also a lot of problem with dealing with wind. The nice thing is scaling starts to really help you as you go to small scale because the mass, as wingspan goes down, mass goes down much faster than the area you have available because of the scaling of surface area to volume. So if you look at down around about a gram and lower, insect-sized robots start to have solar arrays that need solar arrays that are smaller than the wingspan. So this suggests that solar power starts to become viable as you go to very small scale drones. So then you can imagine these potentially flying indefinitely in the sunshine. Okay, so let me just summarize what I've told you. So insect robots will have application, but you have to have a good reason for them. So the applications I foresee them being applied in will come where small size is a distinct advantage. These include, for example, where large swarms are needed to be deployed to collect very detailed information about the world, or the robots need to navigate very confined spaces, like in piping infrastructure, for example. The key challenge with making insect-sized robots is that the physics changes with scale, but it also represents an opportunity for new capabilities in robotics that are not possible with larger robots. I told you about a lot of significant progress, but there's much to remain, particularly in the area of sensor autonomy. And by and large, solutions to a lot of these problems have been and will in the future be inspired by insects. So I'll conclude by telling you that I've started a new lab at the University of Washington to build and operate these insect-sized robots. Includes manufacturing facilities, including one of these laser micromachining systems, as well as carbon fiber composite facilities, soldering station, and so on. And I'm now recruiting students in the area of visual perception and robot control. So if you're interested, please contact me. I can be found on Google. And with that, I'd like to close by thanking all of my collaborators and funding sources, and thanking you for your attention. Thank you.
Questions for Sawyer? I'd like to thank you for two different kinds of awesome videos. One is the robots and the other are the animals. Just remarkable acrobatics in both cases. I was going to ask about energy storage. So you mentioned solar power as a possibility, but we know that houseflies or other bugs are operating from chemically stored energy.
Yeah.
Is there any possibility of engineering some kind of special battery or something like that that would make that possible?
So flies can indeed fly for hours without eating. So that's the proof of concept. I would love to tell you that there's some reason why the small scale makes it more possible than at larger scales, but my hunch is that if we could come up with a technology to turn fat stores or glucose stores directly into electricity, that would be a huge discovery for any scale thing. So I don't think anything is different at small scale, but that would be great. That said, the other point I would make is that we could probably expect 5-ish minutes of flight time with battery power. So that's the other side. You could potentially combine solar with battery, or of course, I'm also very interested in exploring wireless power as well, of course, which there's a lot of experts here at UW on wireless power. So, yeah.
So if you just treat the fly as a battery, I mean, how does its energy storage compare to that of the best, its energy density compared to that of the best batteries?
My understanding is that the power used by the robot fly is about equivalent to that of an actual bee that weighs about the same weight, 100 milligrams. So I think from there you can probably easily extrapolate and say that if I think the number I know of is, I'm not sure exactly. I think a horsefly, maybe a bee is the same thing. They can fly for I think something like 12 hours. So you can extrapolate, because we know that the bee uses about 20 milliwatts. So multiply that by 12 hours. That gives you a sense of how much better this fat stores on insects are relative to batteries. And I think the number is, it's probably like the difference between gasoline and difference between gasoline and batteries, which is like 100 times or something. So yeah, so that would be great to be able to do that, maybe with fuel cells or something.
I guess I have one last question. Another capability we have here at UW is pretty talented chip design group. What are the power electronics challenges for driving these actuators? And if you're a circuits person, how would you look at that problem?
Yeah, that's a definite challenge that I didn't get into here. So the piezos require high voltage, about 200 volts. And so this requires a boost converter of some sort and a tiny coil typically, as well as transistors that can tolerate the high voltage. My initial take on this is that I would probably use discrete components. Rob's group at Harvard is working on a kind of an integrated solution. I don't know if it's working yet, but yeah, I think that would be great to have a kind of a turnkey solution there. But it will be very much, I think, driven by the specific needs, I think, of this application. Like maybe there's simplifications you can do if you know that you're flapping at 100 hertz, just because the whole task is to flap it, drive a sinusoid voltage at about 100 hertz. So maybe there's tricks you can do there. I'm not sure. Yeah, I'd be very interested in solving that problem. Yeah.
Great. Well, thank you very much, Sawyer. Thanks for coming to talk to us.